Okay, let's keep going from where we left off in the last video, talking about these methods whereby if we're working with a continuous function on a closed interval, we can locate the global maximum and minimum and figure out what that global maximum is going to be, more importantly, by just taking a look at each of the critical points in that interval as well as the endpoints. So we looked at an example last time of doing that, and I want to just glance at another example really quickly as well. So let's suppose that this time, and let me dig out my pen here, because I obviously need to have a working pen. Did I leave my working pen here? Perhaps that's what happened. Well, this looks like it's working okay. So let's try doing the same thing, and let's see if we can find the global maximum and minimum for, and let me make sure that I'm doing the function that I actually wanted here. F of x is equal to x cubed minus x squared minus 6x on the interval from 0 up to 4. So here's what we're going to do. We're going to find all of the critical points. Now remember, the critical points are the places where the derivative is 0 or is undefined. And then we're going to see which critical points sit inside this interval. And then we're just going to check the function at the endpoints and at the critical points inside the interval. It's actually, it seems like maybe a complicated process when you first see it, and it can take a bit of time to get used to. Once you get used to it, it's really actually a pretty straightforward process to do. Now, the nice thing about this function is it is a polynomial. Therefore, it is differentiable everywhere. So we don't have to worry about there being places where this thing fails to be differentiable. We're all set in that sense. All we have to do is look for where the derivative is 0. Well, the derivative is very straightforward to calculate. 3x squared minus 2x minus 6 gives me my derivative. So now I want to set this thing equal to 0 and solve it. Now, I'm going to be honest with you. I am not really very good at factoring things. I kind of suspect this might factor. And if you like messing around with factoring, you can. But I personally would just use the quadratic formula at this point, because you may as well. I feel like, for me at least, that's as fast as I can do it. Now, if you want to see if you can factor this by grouping or something, be my guest. I think we'll see in a moment whether there's a way to do it. But you may as well use the quadratic formula, I think. So this is going to give me 2 plus or minus the square root of negative 2 squared minus 4 times 3 times minus 6, all divided by 2 times 3. This is going to give me 2 plus or minus the square root. Sorry, that is a ridiculous looking square root. This is going to be, for one thing, I'm going to keep coughing apparently. I've got something stuck in my throat. 12 times 6 is going to be 72, plus 4 is going to be 76. Oh, this doesn't factor by grouping. Okay, I was wrong. Divided by 6. So this is going to be 2 plus or minus the square root. Now let's see, 76 is divisible by 4. It is 19 times 4. So this is 2 plus or minus 2 times the square root of 19 divided by 6, which comes out to be 1 plus or minus square root 19 divided by 3. Now, which of these two numbers sits between 0 and 4? Well, the answer is 1 minus square root 19 is a negative number. So 1 minus square root 19 divided by 3, this is less than 0, and it is not in this interval. For that reason, I want to ignore this possibility. I mean, it's not that we want to ignore it totally, right? We found it. It's just, it's not in the interval that's of interest to us. So we're going to forget about it from this point forward. The one that is inside this interval is going to be 1 plus radical 19 divided by 3. Now, how do I know that's inside the interval? Well, the square root of 19 is somewhere between 4 and 5. That means that 1 plus the square root of 19 is somewhere between 5 and 6. If I take a number between 5 and 6 and divide it by 3, I get something close to 2. It's a little smaller than 2. Well, that is definitely inside the interval from 0 to 4. So this is, in fact, going to be a critical point that is inside the interval here. And by the way, your book calls them critical numbers instead of critical points. Both are correct, but the term critical point is a little more general. So I like to use the term critical point because later on, if you go on to take, say, Calculus 3, you'll learn about how to generalize this stuff into higher dimensions and talk about critical points for higher dimensions and things. And then you gotta call them critical points rather than numbers. So we may as well start now. Okay, so now we found the critical point. Well, everything else is just a matter of evaluating this thing, okay? So we're gonna evaluate this thing at the endpoints, and we're going to evaluate this thing at the critical point, and we're going to see what we get. Now, if I take f of 0, that's the first endpoint, that is going to give me just 0, because everything here is multiplied by an x. If I take f of 4, this is going to give me 4 cubed minus 4 squared minus 6 times 4. Now, this is going to be 64 minus 16, which is 48. And then I'm subtracting another 24. 48 minus 24 is actually 24. And then we're going to be plugging this thing in. Now, we can work out what this comes out to be, but then we're going to have to figure out whether it's the biggest or the smallest. And so let's take a minute to work out what this is going to be, first of all. And to be honest, this is going to be one of those cases where I am just going to plug this into a calculator because I don't really think that it is worth, like, we can work out exactly what this is, but I would say let's just plug it into a calculator in this case, and we'll give a decimal estimate for this problem, since it really doesn't have any nice answers. Normally, I know I'm against decimal estimates, but I don't feel like taking the time to cube this by hand, or even square this by hand. So let's just plug it in, and I'm going to do that. You can do that. I'm going to pause this while I plug it in. And if you use a nice computer calculator type thing, like I used Symbolab right there while I had this paused, they will actually give you the exact answer as well. So this is a nice little trick that you can use. And to be honest, I'm kind of okay in most cases if you use a calculator to do this. You should know how to do it by hand, but doing long calculations by hand is annoying, so I don't really mind if you throw things like this into a graphing calculator that can give exact answers. It comes out to be negative 56 minus 38 times the square root of 19, all divided by 27. Now, this is approximately negative 8.8. Wait, 8.8? No, I'm sorry, 8.2. I can't read. Well, I can read. I can't remember what I've read for 2 seconds, apparently. And I know, even without looking at the decimal approximation, that this has got to be the global minimum. Because our first possibility is 0, and our second possibility is positive. And whatever this comes out to be, it is negative. So this has to be the global minimum, even before I see that it's around negative 8.2. So this is going to be my global minimum, and this is going to be my global maximum. So there we go. We have figured this out. Now, here's just a really quick example, and we will return to this later, but you might ask yourself, where does this kind of thing come into play in practice? Well, here is an example of doing this kind of thing that will sort of show you where this kind of thing is useful. So let's suppose that we want to build a rectangular pen with 16 feet of fencing. what is the largest area we can make? Well, with what we've said so far, we can actually answer this question in a fairly straightforward manner. Because here's the thing. I'm going to say, let's make the dimensions of this rectangle. I'm going to make the base of the rectangle a length of x. If I do that, the top of the rectangle is also a length of x. And that means that these two sides are going to have to be 8 minus x. Now, why is that the case? Well, because these two sides together, all four of these sides need to add up to 16. And so if these two sides total to 2x, then these two sides need to be 16 minus 2x. But each of these sides are the same length, so they're exactly half of 16 minus 2x. So that's where these numbers come from. And then what we can do is we can say that the area is going to be equal to x times 8 minus x, which is equal to negative x squared plus 8x. And then what we can say is there's a little bit more here. You see, what we can say is that 0 has to be less than or equal to x, which has to be less than or equal to 8. Why can we say that? Well, the reason is because we're using 16 feet of fencing. And the smallest that I can make this bottom edge is 0. I could theoretically just lay both pieces, like make two line, like literally just make a one-dimensional fenced-in area by putting two pieces of fencing right next to each other. The other option would be I could expand that side all the way until this base and this top become 8 feet long. That means that instead of putting two pieces of fencing vertically, I put them horizontally, but it would be the same kind of thing. And so the domain for x is going to be 0 up to 8. And then what I can say is, well, the derivative of area with respect to x is going to be equal to negative 2x plus 8. And if I set negative 2x plus 8 equal to 0, I get x equals 4 as my critical point. Now, the interesting thing is that if I take the area at x equals 0, I get 0. If I take the area at x equals 8, I also get 0. Right? Because 8 minus x is 0, so it's pretty quick to evaluate. If I take a of 4, I get 4 times 4, which is 16. This is therefore the largest that I can make the area, and it is 16 square feet. Now, we're going to return to these kinds of optimization problems later, but I wanted to show you why this kind of thing is of interest to us, not just from a mathematical perspective. It's very interesting mathematically, of course, but it's also actually a practical kind of question as well. Of course, this one, maybe you could have answered this without using calculus, right? And the reason you could have answered this without using calculus is because this is actually just a quadratic. Quadratics we know how to handle if we want to find their maximum or minimum because we know how to find their vertices using algebra, right? You basically complete the square and that shows you how to find the vertex. You may remember doing this if you think back to algebra or pre-calculus, maybe you did that kind of thing in there. So technically for this one, maybe we wouldn't have needed to use calculus, but calculus makes it really, really easy to do, maybe easier than all that algebra. Maybe not, I don't know, it's not like the algebra is that bad. But I wanted to show you how we can do it with calculus, because what if now I have some other scenario where things are more complicated, where we're not just working with a quadratic, where we're working with some more complicated function and trying to optimize things. So the point is that these kinds of ideas, yeah, they really are going to help us extensively in the future when we start talking more about practical optimization questions. All right, so we've talked now about how we can find global maximums and minimums. Now, it turns out that a lot of our questions are going to revolve not so much around finding global maximums and minimums, but around finding local maximums and minimums. And one of the reasons for that is because these local maximums and minimums are going to help us understand the behaviors of functions. So if I want to sketch a graph of a function, understanding its local maximums and minimums is going to be really, really crucial. And so how do we go about finding these local maximums and minimums? Well, before we go into first of all, the thing that we want to observe is that local extrema, remember, an extrema just means a maximum or a minimum. Why it's called an extrema? Oh, extrema is like the plural. Extremum is the singular, but local extrema occur only at critical points of the function. So this is a very interesting point because it tells me that the largest number of local extrema that I have is given by the number of critical points. Now, think back to pre-calculus where you were told that the largest number of local maximums and minimums that a degree n polynomial can have is n minus 1. Well, this tells us exactly why. So notice, if p of x is degree n, then p prime of x is degree n minus 1. Well, here's the thing. An n minus 1 degree polynomial is defined everywhere, so there's no places where this derivative is undefined, but also it's degree n minus 1, and therefore p prime of x has less than or equal to n minus 1 roots. But that means that p of x has at most n minus 1 critical points, and therefore it has at most n minus 1 local maxima and minima. So that fact that you were told back in pre-calculus probably is actually really easy to prove using calculus. To be honest, I'm not even sure if there is an algebraic way to prove it without going into calculus because, well, the thing is that because it's so easy to prove with calculus, I've never bothered to look into whether there's a direct algebraic way of seeing it. Because, you know, it falls out of the calculus stuff almost immediately. The only thing that's even slightly tricky here is to prove that p prime is degree n minus 1, but that's actually very straightforward. Just take a look at, write down a general degree n polynomial, write down its derivative, and you will observe it decreases the degree by at least 1. In fact, it should decrease the degree by exactly 1, I should say. Sorry, I said at least 1, but exactly 1. Okay, so now how do we decide if we have a critical point? How do we know whether that critical point is a maximum or a minimum? Well, here is sort of the direct way of figuring that out. We're going to notice that a function can only turn around at its critical points. So it can only switch from being increasing to decreasing or decreasing to increasing at critical points. So let me remind you that f is increasing on some open interval a to b if for any x1 and x2 in a to b with x1 less than x2, f of x1 is less than f of x2. And it is decreasing, then you switch this around and we say f of x1 is greater than f of x2. So I'm not going to rewrite the entire definition because it's literally the same definition, just you flip the direction of the inequality. Now, here's the thing. We can only switch at critical points. And the reason is because if I switch from increasing to decreasing, well, more to the point, if I have like a local maximum or something, then I go from increasing to decreasing, or maybe I go to being perfectly constant. But the idea then from this is the following. If I have a critical point, let's say I've got a function and I have a bunch of critical points. So let's say that we have f of x, and I'm going to make a number line here and say here's like C1, C2, and C3. And these are going to be critical points of f. Now, what I want to say is, suppose that there are no critical points between C1 and C3 except C2. So this is the only critical point in here. Here's how I can figure out, is C2 a local maximum or minimum for this function? Well, here's what I'm going to do. I'm going to pick 2 points in here. I'm going to pick a point A and a point B on either side of this critical point C2. Now, the important thing about picking these points is that there needs to be, in this region here and in this region here, in other words, in the interval between A and B, C2 has to be the only critical point in here. Right? So I cannot have other critical. If I picked A to be way over here, that would be bad. The key point is I want to make sure that there's no other critical points in here. And as long as there's no other critical points in here, I can pick whatever points I would like. It really does not matter at all. So if I do this, then what I can do is I can say, okay, well, now what I'm going to do is compare f of A, f of B, and f evaluated at this critical point, C2. And then what I can do is I can say that if f of A and f of B are both bigger than f of C2, this means that what we have is a local minimum. Why? Because in that case, what we're saying is we have something down here at C2, then we've got something up here and something up here. So that means we're coming down to a minimum and then going back up. On the other hand, if I have f of A and f of B being less than f of C2, then this means what I have is a local maximum. Why? Well, it's exactly this picture, but flipped upside down. Now what I've got is I have the function evaluated at C2, I have the function evaluated at A and B, and it's the same picture, but upside down. Finally, what we can say is that if one of them is bigger and the other is smaller, then this is neither a local maximum nor a local minimum. So where can I write that? Well, you know what? I'm just going to have to erase this picture at the top because I don't have any space. So you still have that picture in your notes, I hope, and therefore what we can say is if f of B is bigger than f of C2 and f of A, I wrote f of A, I said f of B. If f of A is bigger than f of C2, f of B is smaller than f of C2, then this means that what we've got is neither. And same thing goes if we have f of B bigger than f of C2, f of A less than f of C2. Well, once again, this is neither. Now, again, the important thing here is you got to pick your test points so that the critical point you are interested in is the only critical point between them. That's really important. Like, super important. If you don't do that, then this test is not going to necessarily work for you. There's no reason to expect it to work. But as long as you've only got the one critical point in there, then that's fine. The other thing that I want to say is that if f is continuous, and this is important, if f is continuous, then you could actually pick A and B to be a critical point on either side, as long as there's no other critical points between them. So in other words, I could have picked A equals C1 and B equals C2 is okay if f is continuous. But if f is not continuous, you don't want to do that either. You got to be more careful in that case. So normally we're going to be working with continuous functions, normally, but sometimes we won't be. Like, we're going to be working with some rational functions. Rational functions are not, they're continuous on their domains, but they have these jumps in their domains. And so in those kinds of cases, you want to be more careful. So it's okay to pick the other critical points as your other test points, but only if your function is continuous. So let's take a quick look at using these ideas to decide whether something has a local maximum or minimum. Now I want to show you, first of all, how we do this in a case where we already really know the answer. Because it's always good to kind of see what happens in the cases where we already really know what's going on. That way we can say, oh yeah, this is what we expect. Everything makes sense. And so that's always a good thing. So let's say that we want to find all local maxima and minima for, let's say, f of x is equal to negative 2x squared plus 3x plus 7. Well, the way that we're going to do this is we could say, yeah, this is going to have a local maximum at its vertex and no local minimums because it's a parabola and it's upside down. So we sort of know the answer already, but let me show you how to do it with calculus, and then we'll see how we can use these calculus methods in cases where we don't already know how to do this stuff. So f prime is always defined, there's no problems there, and then we get negative 4x plus 3. If I take negative 4x plus 3 and set that equal to 0, I'm going to get x equals 3 over 4. This is my only critical point. Now, it can be helpful when you're picking test points to mark your critical points on a number line. So we may as well start doing that. And I'll mark that this is a critical point at 3/4. There's no other critical points though, so it's maybe not super important in this case, but we may as well start doing this anyway, since we're going to be using it in the future. Now I need to choose test points. Now, some good test points, in my opinion, would be 0 and 1, because, well, they're pretty easy to evaluate things at. And then we just have to ask ourselves, okay, so what is f of 0? Well, that's going to be equal to 7. What is f of 1? Well, that's going to be equal to 10 minus 2, which is 8. And then, what is f of 3/4? Okay, this is going to be the tricky one. We're going to have negative 2 times 3 over 4 squared plus 3 times 3 over 4 plus 7. This is going to be equal to, let's see, 9 over 16 times negative 2 is negative 9 over 8. Then we're going to have plus 9 over 4. And then we're going to have plus 7. So this is actually 7 plus 9 over 8, which is going to be 8 and 1/8, or 8.125. Now, normally I don't like writing things in decimals, but I'm writing it out this way just to emphasize, oh, look, this is actually bigger than 8. If I wrote this as a fraction, I could write this as 65 divided by 8. And we can see, well, 8 is 64 over 8. So this is actually the largest value of these three. And what that tells me is that at 3/4, what we actually have is a local maximum. But as I said, this is the only local maximum that we have got. We don't have any local minimums either. Now, this is not surprising because, like I said, this is a parabola. Parabolas, it's an upside down parabola, in fact. So we know it's got exactly one maximum at its vertex, and that's it. You could say using calculus to solve this problem is sort of like, using a huge pack of TNT or something to unlock a window. But, it's way overpowered for what we need. But it's a good example of how this works. And to be honest, it's not like it's actually that difficult either to figure this out. In fact, if you want to locate the vertex of a parabola, using calculus is not necessarily a bad way to remember how to do it. The vertex of a parabola occurs where the derivative of the parabola is equal to 0. Now, of course, you can just memorize the minus b over 2a formula if you want to, but you can get that formula really easily this way as well. But I digress from what we're really focused on here. So we can also do this in more complicated cases where it wouldn't be so obvious algebraically what is going on. And as an example of this kind of thing, we could say, let's try to figure out, and give me a second here to get the example I want. All right, here we go. So let's see, and I want you to pause the video and take a few minutes to try to solve this on your own. Find all local maxima and minima for the function g of x is equal to, let's make sure that I've got this right, we're going to have 2x cubed over 3 plus 5x squared over 2 minus 12x plus 2. And in this case, before you start into this, let me just remark, well, this is not a parabola. This is a degree 3 polynomial. So we would not be able to solve this using the methods that we have from pre-calculus. This is one where calculus is actually, again, maybe there are some crazy algebra tricks that you could do, but calculus is really the best way to go here. So take a minute, see if you can do this, and then we'll work through this together. Okay, were you able to come up with anything? So the first thing we want to observe here is, what is g prime of x? So this is equal to 2x cubed plus 5x squared minus 12. Now, I specifically chose this example because it's relatively simple here to, like, the derivative is kind of nice. And what I mean by this is that this actually factors into 2x minus 3 times x plus 4. And if you didn't see that it factored this way, then you could just use the quadratic formula. But I'm going to use the fact that this thing factors and do it that way, just because it makes it really easy. So we take this and we set it equal to 0. This is going to give me 2x minus 3 equals 0, or x equals 3 halves, and then x plus 4 equals 0, or x equals minus 4. So these are my two critical points. And if we make our number line here, we're going to have a critical point at 3 halves, and we're going to have a critical point at negative 4. So now the question is, what do we want to do for our test points? Well, I'm going to choose a test point at 0, a test point at, let's say, minus 5, and a test point at, let's say, 2. Because remember, all I really need to do is to get one test point on either side of each critical point. And we may as well use these. Whoops, that should be a negative 5, not a positive 5. So now we just got to go through and evaluate this thing at each of these points. So let's see what we end up with. And once again, I'm going to actually be kind of lazy here and sort of just evaluate these things using So if we do f evaluated at negative 5, what we end up with is we end up with 875 over 6 minus 58, which is approximately 87.8. And the reason I'm looking at this approximation is because we're going to use this then to compare this to the other numbers. Now, if I do f evaluated at -4, then we're going to get oh, shoot, I just did -5. I'm sorry, I plugged in the wrong thing here. Let me back off on that for a second. So I just did f evaluated at 4. This becomes 104 at -4. So f of -4 is equal to 142 over 3. Now, if we do -5, which is what we were supposed to do, I did +5 there, so that was my mistake. And a good reason why, even when you're using a calculator to help you, you got to be really careful. If I do this one, I end up with -125 over 6 plus 62, which is approximately equal to 41.2. And then if I do f evaluated at 0, well, this is going to be equal to +2. Now, what is 142 divided by 3? Well, 142 divided by 3 is going to be 47 1/3. So we see that at this critical point, f is larger than it is on either side of the critical point, and that makes this into a maximum. So there we go. That part is done. This is a maximum, a local maximum. So we started by picking a point on either side of the critical point. Then we evaluate the function on either side and at the critical point, and we see, oh yeah, if I look at this, at the critical point, that is the largest of the 3 values. That means it is a local maximum. So now, if you weren't able to get this far before, take a minute at this point and try to work out what happens with this other critical point over here and see what you can get. All right, so let's look at this other critical point. Now, what I'm going to do here is I'm going to make things easy on myself by reusing 0 as a test point. So we know f of 0 is equal to 2. So then if I do f evaluated at 3/2, once again, I'm going to be lazy here and just throw this into a calculator so that I don't have to do this by hand, although you should be able to do it by hand if you need to. This comes out to be -65 over 8. And if we then evaluate it at 0, we have 2. And if I evaluate this at +2, well, that's even easier, but once again, we're just going to use the calculator here, because I'm feeling particularly lazy about doing these things by hand today, and I have it with me, so I may as well. This comes out to be -20 over 3. Well, of all of these, f of 3/2 is the smallest, and therefore this is actually a local minimum. So our answer is that we get a local maximum at -4, and we get a local minimum at +3/2. Now, one of the things that this tells me, if you look at a graph of this thing, this is not too surprising. And the reason is because if you look at a graph, what this comes out to look like, and I'm just going to give you a really, really rough sketch here, it looks something like this. So it ends up doing this kind of a shape. It's actually more like this. And then this maximum occurs at -4, and this occurs at +3/2. Now, the thing about this method for finding local maximums and minimums is that it's kind of annoying. It takes a lot of work. So what we're going to want to do next time is we're going to ask, are there any shortcuts that we can do that will help us to determine if something is a local maximum or minimum without having to do all of this work? And the answer is yes. There are some really nice tricks that we can use with calculus that will make these problems easier for us. But for now, I'm going to leave things there. Let me know if you have any questions, and we'll come back to this soon.